Okay, so let us start. Okay, so we had a distribution which is a Gaussian distribution, remember, in the last class, and I think we found this to be 1 over twice pi sigma square exponential of minus x square by sigma square. So if I want to make it more general, then I can say, okay, my distribution is not peaked at x equal to 0. Okay, so my average x is non-zero, and I'm calling it mu. Okay, so my average x is non-zero, calling it mu. And then I can write down this distribution. This distribution is going to be it is not very difficult to understand, isn't it? I hope you can follow.
Yes, sir.
Okay, so it is not very difficult to see. So how can you check whether this is normalized? I should be able to check, na?
Integral px dx equal to unity.
Is it normalized? Yeah, it is not very difficult because you can check it just by saying, okay, your x
X minus
minus
mu
mod
equal
x,
to
which is your x minus mu, this is equal to something like, say, I call it y. Then it's obvious, no? Your dx is, you know,
dy.
yes, dx is dy. But yeah, dx is dy, and dx is dy, you're right. But one more thing you can do, I'm not going to do everything in so your sigma x square, you remember sigma x square? Your sigma x square was uh, uh,
X square average minus x average square.
yeah, x square average minus x average square. So this is your variance. Okay. So rather than taking this is y, I'll do something else. It's easier if I take the whole argument as y. Okay. So I can just call it this x minus mu by root over 2 sigma x is equal to y. So that the whole argument is y square, x is exponential of minus y square. Is this clear? And if I do so, then what is dx? Dx is going to be equal to, tell me,
Root 2
dy
sigma.
times root 2 into sigma x. So your p of x dx, what will happen to the limit of integration? See, it is minus infinity plus infinity, so it does not really matter, isn't it? The integration limit is not going to change. Okay, and your what is your py? Py is it is 1 over root over, okay, let's 2 pi sigma x square. Let me keep it like this, and this is going to be exponential of minus y square into dx. No, what is dx? dx is root over 2 sigma x into dy. So I can take all this common. So essentially what you have is root over 2 sigma x divided by root over 2 sigma x into root over pi, isn't it? And I have this integral. If I do any mistake, let me know. Huh? What will be this integration? You remember? Exponential of minus
Root
alpha x
pi.
square. Yes, is root over pi by alpha. So this one will give me, you have 1 over root over pi, okay, and it will have root over pi. So this is going to be 1. So it's normalized, okay. So I proved normalized. There is nothing to prove actually. That is normalized. Okay.
Yes, sir.
What about mod x? You can actually go and check that your mod x is actually equal to mu. You can just back calculate and see mod x equal to mu. And also you can calculate x square average. Any idea what this x square average is going to be? Any idea? This x square average?
Sigma square plus mu square, I think.
Yeah, it is going to be sigma square plus mu square. You can check. How do you check? Any idea? Maybe I'll show you. It is not very difficult. So let us assume again that okay, your x minus mu equals to say z, some variable. Then what is x? X is z plus mu. Your dx is dz. So your mod, sorry, not mod, average of x, which is this, xpx, no? This is going to be z plus mu, okay, z plus mu e to the power of minus z square by 2 sigma x square. Oh, this is fine. This is fine with you?
Yes, sir.
And of course, you have a normalization constant, which is 1 over root over twice by sigma x square. What is this? If I do the integration, I have two integral actually. And integration is over z. Okay, so the first integral I have, this is common. This is common. So the first integral is z okay, this is the first integral. Okay, now this first integral plus you have, yeah, you're right. I'm doing it because you guys should get used to with this kind of integrations, and mu will come out and you have okay. So what is going to happen here?
Odd integrand, so 0.
This is 0, odd, and what about this quantity?
Unity.
This is all normalized, no?
Yes,
So
sir.
it is unity. So what is the answer? Answer is mu.
Mu.
So we have proved that average x is equal to mu. Got it, no? Should not be a problem. What about the next thing? That sigma x square. So let us do it. So let us calculate x square average first. If you calculate x square average, you know the answer. This is x square average is x square into 1 by. Now you'll have it is equal to minus x square by 2 sigma square, isn't it?
Yes, sir.
Yeah. I hope you can understand. So next term would be I express x in terms of z. What is x in terms of z? Tell me. It is actually z plus
Zero
mu
plus 2.
whole square. What about here? Okay. Is this clear?
So the probability
Sorry.
distribution is x minus mu in the exponential, right?
Sorry. Yes. It will be just z square. You're right. And here it will be x minus mu. If I type something wrong, you should tell me, because it is important that. Okay. I think I'll just write it again because it doesn't look nice. Hope this is fine now. Huh? So what is the first integral? There, how many integrals are there?
3.
Okay, the first one is going to be z square, whatever, 1 over twice by, that is common. Anyway, sorry, not calling sigma x itself, not changing the notation. Doesn't matter. This is the first integral.
Yes, sir.
Okay, I'll have another integral which is something like, say, mu square into this. If I do anything wrong, tell me. Huh? What about other integral, which is twice
2
mu?
mu.
Now tell me how to do. Now this is very nice, na? The second one, the third one
Okay.
rather. Yeah,
Third one is 0.
this is
Again.
0. What about the first and second one?
Second one is again only mu square.
Now second one is also mu square because this is normalized. Na?
Yes.
This is very nice. Once you do this, so what I have, end of the day, I have this, your x square average is equal to mu square plus an integral, isn't it? What is the integral? Integral is okay. So let us, I am just doing it like may not like it. It is, but let me do it. Okay. So let call this as z tilde. Huh? Then dz equals to root over 2 times sigma x into z tilde. So this integral will become what? 1 over whatever I can just. I'm not changing this sigma x square. Keep it like this. Okay. So your should be dz. See, I have to put dz. 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 Huh? This is very important that you put dz. Okay, so this integral, now what is z square is what? Z square is z tilde square into
2
2
sigma x square.
sigma x square. What about this? This is exponential of minus z tilde square dz tilde. So what I have here is 1 by root over twice pi sigma x square.
So dz tilde into root 2 sigma x, no?
Uh, no, this one is whole is z tilde, no? This is z tilde.
Yes, but in the substituting dz with dz tilde,
Yeah. Sorry, you're right. We are substituting dz tilde, so it is root over 2 into sigma x has to be. Yes, you're right. Root over 2 into sigma x. This is what you're saying, no? So essentially what I have here, is this clear? Or the other way?
yes, sir.
This is fine, na? This is fine?
Yes, sir.
I guess so.
Yes,
Yeah. So basically what you have here, 2 sigma square into root 2 into sigma x. Okay. So basically this sigma x square, this will cancel, this root 2 will cancel. So essentially you will have 2 by root over pi into sigma x, no? And then you have this integral. Integral is z tilde square e to the power minus z tilde square dz tilde. How many of you remember? Let me write down. If you have expression like this, we had derived in the last class, no? The integral.
It will be 1 upon 2 into root pi alpha.
I think this is how I remember, okay?
Yes,
Isn't
sir.
it? Alpha is 1 here. So it is 1 over 2 to root pi. What is
that will
this?
be sigma x square in the
Yeah. This is sigma x square. Yes. So this is going to be what? This is going to be sigma x square. So your x square is mu square plus sigma x square. Okay? This is fine.
yes, sir.
Yes, sir.
So you have checked. So just because this is a good practice, because you'll be solving assignments which I'll give you hopefully this weekend or early next week, and then you can start solving assignment. But after this, now we move to discuss what is known as microcanonical ensemble. Now microcanonical ensemble is like something like this, that you have a box filled with many particles. This is your system, and the box has wall. The wall is such that the wall does not allow you to exchange any particle with the surrounding or any heat with the surrounding, and no work is done on the system. So your heat change is 0, work done is 0, so your change in internal energy is 0. So this is actually representing what is known as isolated system. Okay, and you have say n number of particles or molecules. V is the volume and E is the internal energy. So these are fixed. So this is your macro state of microcanonical ensemble. Okay, clear?
Yes, sir.
Now, This is microcanonical ensemble. Now, you know that this macrostate can come from several microstates, isn't it? There's no unique microstate. Many microstates can give rise to this macrostate. Okay, this is fine. If I say like this should be fine, no? So now let me illustrate this with a picture. Okay, with a picture, let me illustrate this concept. What is the concept? Say I say my system is such that I have 4 particles. And 4 energy levels I have. That is my system. So 4 energy levels mean like this. And energy levels are such that the energies are in some arbitrary unit 0, 1, 2, 3. And I give you that your energy, total energy, has to be in some unit equal to 1 in that unit, 8 in that unit. Okay? Is this clear?
Yes, sir.
So now how can I put these particles in this whatever in this system? So one way that I put the one particle here, one particle here, one particle here, one particle here. What is the total energy then? 3 plus 2 plus 1 plus 0.
6.
So it is not acceptable. Okay, so not acceptable. Is this clear what I am saying?
Yes, sir.
So, but because I have told you that total energy is 8. So this kind of arrangement is not acceptable. So this microstate does not belong to this ensemble. Is this clear? If I fix my
Yes, sir.
energy as 8. So what will be the solution? The solution will be something like this. Okay. Have to be careful. We'll have situation like this. So rather than this, we can have situation like same energy levels, but now I put one particle here, other one here, and 2 here. What will be the energy then?
8.
8.
So this is allowed? Huh? So I can have some other arrangement also. Can anyone suggest me another arrangement?
All 4 of them in E equal to 2.
1, 2, 2, 3.
This is one. One is saying that 1,
2,
2.
2, 3.
What is that? 1, 2, 2, 3 is what? There are
1
4
in
particles.
1, 2
Yeah,
in
so
2
1
in
in
1.
1, 2 in 2, 1 in 3.
Two
Yeah, this
particles in 3, one particle in 2.
No, 2 particles in 2, 1 particle in 1, 1 particle in 3.
I think this is one possibility, of course, because this is 3 plus 3 plus 1 plus 1. What about this? This is 1 plus 2 plus 2 plus 3. This is 2 plus 2 plus 2 plus 2. I think these are only 4 possible arrangement, isn't it? In this case, check.
Yes, sir, probably.
Yeah. So, but the message is as follows. The message is that each of them represent what? One microstate, isn't it? You got it?
Yes, sir.
Each of these arrangement represent a microstate. So each of this represent a microstate. So there are 4 microstates. Is this clear?
Yes, sir.
But all of them give you the same macro state. Is this clear? This is very important. Because I am sure that it is done in 408. Kailash, are you there?
Yes, sir. It is done. It is done, sir. In the
So do you understand what I'm saying?
Yes, sir.
Okay. So now I go back to what we taught, what we learned in the last class. Uh, Postulate of equal a priori. Okay. So postulate of equal a priori. What is that? It tells you that if your system is in microcanonical, if you are in microcanonical ensemble, then then all the microstates corresponding to that ensemble are equally probable. Remember?
Yes,
Yes,
sir.
sir.
So if I say that your omega, which is a function of n, v, and e, this is number of microstates. Then inverse of omega will give you something like a probability, and isn't it?
Yes, sir.
Of finding okay, this is one way of saying the probability of finding the system in ith microstate. So now I go back to a gentleman called Gibbs, who proposed the following formula for entropy. He said the entropy is given by this. Okay, which is nothing but your minus kb times average of ln p. P is probability. The probability of finding the system in that ith microstate. This is Gibbs entropy, and is also known as, I don't know whether you know, this is called Shannon's entropy. It's very similar to what is known as Shannon's entropy. Of course, in Shannon's entropy, you don't have kb maybe. Kb is there to take care of the dimension. Kb is the Boltzmann constant. So we'll take this formula. Okay, we'll take this formula. Now, if we take this formula for microcanonical ensemble, what will happen to entropy? Minus kb sum over I. What is
1
pi?
over 1 over omega.
Omega. I'm not writing nv again and again. Ln.
1 over omega.
What is the answer? See, 1 over omega and sum over all possible microstates. Okay, that'll give you some number of microstates. And if I sum over all possible microstates, that will give you omega essentially, isn't it? So
So
this is
log
going to be omega by omega into ln1 minus ln omega. Is this clear? What is the answer? Answer is AS is
AB log omega.
kb ln omega. So this is the expression for entropy in microcanonical ensemble. I hope that you knew this. And this is also known as Boltzmann expression for entropy. Does it look familiar? Have you seen it anywhere else?
I think in the discussion of third law of thermodynamics.
Yes. So the third law means that if for a purely crystalline substance entropy is 0, that is only possible when your omega is 1, isn't it? Only one microstate possible, isn't it? So only one
Yes, sir.
at low temperature 0 Kelvin, I can have only one microstate, only one arrangement. There will be all the particles in the ground energy level, isn't it? And then what will happen to the entropy? Entropy will be 0. Of course, it's 0, but within a additive constant. But that additive constant, we take it as 0. So the reference is also 0. Okay? This is the third law of thermodynamics. But these conjectures are all very qualitative. Okay? And the definition of omega, what I've said here, it is very qualitative. Towards today's class, end of the today's class, or maybe next class, we'll again come back to this omega and discuss it in detail, and will go much deeper. Okay, because this omega is related to the volume in phase space. Is it done, this volume in phase space idea of omega in 408 MSc students? Was it done? Kailash, anyone?
Yes,
is there?
sir. Yes, sir. It is done, sir. Actually.
You understand my question? That how omega is related to the phase space volume? Then tell me how it is related to the phase space volume.
Sorry, sir. I have not remembered.
I don't think it is done. This is
I think omega increases with increase in volume.
Yeah, we'll see that, but not today, maybe later. But let us do something else. Okay, let us do something else. So what I do here, I go back and revisit a little bit of thermodynamics. But before we revisit a little bit of thermodynamics, we will revisit what is known as cyclic relation in calculus, a cyclic rule of derivatives. How many of you remember?
Exactly what are you referring to, sir?
The cyclic derivative. If you have, so if I have function of x is a function of y and z, and y is a function of x and z, then one can show that if I take del x del y constant z times del y del z at constant x times del z del x at constant y, this is equal to minus
-1. Sir.
Remember?
Yes, sir.
How many of you can derive this? Don't mug up things. You should be able to derive.
Yes, sir. It can.
So I'll just revisit this because maybe not everybody remembers. So if x is a function of y and z and y is a function of x and z, so the exact differential of x dx, what is this? This is actually dx dy at constant z into dy plus del x del z at constant y into dz. Is this clear? This is equation 1.
Yes, sir.
Similarly, what is the exact differential of y? This is dy dx at constant z into dx plus dy dz at constant x into dz. Isn't it?
Yes, sir.
Is this fine? So now I use 2. So use 2 in equation 1. This will become, your dx will now become, I am writing the second term first. what I have is here dx dy at constant z. Now dy I am replacing. Okay. So dy I am replacing. What I am going to get? I am going to get this. Dy is this. The whole thing will be multiplied with this dx dy dz at z. This is going to be dy dx at z to dx. Okay, is this clear? Is it clear?
Yes, sir.
Class. Can I go back? So this is common actually. This is common, and in state of dy you have this plus this. Okay. So what will be the next term? Actually, I can take this common, and I don't need to take a common. Okay, take it common. But what will be the next term? Here, this one is there.
dy
This
dz.
one multiplied it this into dx. Okay. Then the next thing would be
Del y del z at constant
this
x.
thing multiplied with this into ds, isn't
Del
it?
y del z.
Yeah. Del y del z x dz. This is how it is. Is it fine?
Yes, sir.
Now what is this? Dx dy into dy dx. It is 1. Is this clear? Is it clear? So please tell me whether it's clear. This is 1 into dx actually, of course. Like this part is 1. Look at carefully. X is a function of y is a function of x. So if I differentiate x with respect to y keeping z constant and multiplied by differentiating y with respect to x keeping z constant, this is equal to 1, isn't it? Because this is the inverse of this derivative. Is this clear?
Yes, sir.
Yes, sir.
So what I have here, I have dx that is equal to dz plus then I can simplify it further. What will be, if I simplify, what is going to happen? It is something like, I can write is this fine?
Yes, sir.
Now this is dz is arbitrary, arbitrary small z. So what I can do, I can take this on the other side. What I'm going to get, is this clear now?
Yes, sir.
And this is your cyclic relation. This is cyclic relation. Is this clear?
Yes, sir.
Yes, sir.
So I'll use that. I'll make use of that. So Kailash is not there today in the class, looks like. His internet is down, I don't know.
Yes, sir. He was saying that.
Okay. So now go back. I have three quantities: entropy, volume, and energy. Looking at it, I can write like this: del S, del V at n is constant here, n E into del V del E constant n S into del E, not del E, but yes, del E into del S, del E by del S constant n into V, this is equal to minus 1. Is this clear? I hope I have not done any mistake. Just using cyclic rule. So I suggest you to all of you to go and revisit cyclic rule and thermodynamics a bit, huh? Okay. Now from here I can write that del S del V at constant n comma E is minus 1 divided by del V del E constant ns del E del S constant nv. Also I have this expression, you remember that E equal to Ts plus PV minus mu n. You revise your thermodynamics, you'll see. Sorry, the sign,
Yeah.
I think sign I put wrong.
Sign should be flipped.
Yeah.
PV and
But just sometimes this eraser, don't know what happens. Okay, it has now work. There's a lag. Okay, so if I have this, you should know, if I take del E by del S at constant V and N, this is, what is that? Del E by del S at constant T.
Temperature.
Okay. And del E by del V at constant, say, S and N is minus pressure.
Minus pressure.
And del E at by del N at constant S and V is
Chemical potential.
chemical potential, huh? Okay, chemical potential I have to write. Okay, this is chemical potential line, fine. So now if I do this, what I'm going to get here? I'm going to get minus 1. Now del V del E is what? Is the inverse of that, isn't it? It is minus 1 over P. What about del E del S?
T.
T. So what is the answer?
P/T.
Okay. So similarly, I can do one more thing. What I can do that, keeping this in mind, S and E, I can use the cyclic rule here. I can say that del S del N at constant E and V into, sorry, del N del S del N, then del N del E constant S and V into del E del S constant S constant N and V, this is equal to minus 1. Huh? So similarly from here I can write that del S del N constant EV. What is the answer? -1.
-1 by
Is fine? This is the answer. So can I substitute this now? I have the relations, no? Here.
No.
They are the relations. Relations are here. Nice. Now I can just make substitution. Now if I make substitution, what I'm going to get? I'm going to get del S del N EV is equal to -1 del N del E, which is
1 by mu
1 by mu. What about this guy?
temperature.
Del E del S, it is T. What is the answer?
minus mu by T.
Okay. So now entropy is a function of number of particles, volume, and energy. That you know, no?
Yes, sir.
Yeah. So entropy is a function of number of particles, volume, and energy. So exact differential of entropy is what?
Del S del N dN plus
Yes.
del S del V dV plus del S del ED.
So I am doing it again and again because you should get used to for this course. Then okay, and I had the relation. What are the relation? I had this relation, no? That this is what? Del S del V is this, del S del N is this, isn't it? So I can make use of that. So what I need as del S del N. What is del S del N? Is
Minus mu by T.
minus mu by T. So the first is minus mu dN by T. Now I can make it more general. I can put set, okay, I can make it
Mu I dni.
yeah, something like that, multi-component, huh? I can take this. What about the next term, ds dv?
T by T dV.
P by T.
P by T.
So this one is going to be P dv by T. What about the next term, del S del E?
1 by T.
Del S del E, no, it is 1 by T. So it is going to be okay. Is this clear? Any question? So you can, this is consistent with the thermodynamics. With thermodynamics, you can see. So far we are doing thermodynamics, of course. Just revisiting. Okay.
So
Now what I do, I just use this expression that my 1 over temperature is del S del E into, and this is the definition of temperature, isn't it?
Yes, sir.
We'll talk about it later. The definition of temperature. Okay. Now and this is nothing but what? This is going to be del E of kb ln omega, and this is kb So the nice thing is that if I know omega in microcanonical ensemble, then I can calculate temperature from that. You can see, huh?
Yes, sir.
Similarly, I had, for example, I had P by T. P by T is del S del V. So similarly, I have P by T, which is del S del V at constant. Tell me, what are the constant things?
N and E.
N and E. And this is equal to KB
Del V of log omega.
So similarly, one more thing I can calculate, of course, which I showed, minus mu by T, isn't it? So for example, for the ith component, minus mu I by T is going to be del S del Ni, where I keep E and V and all other Ni constant, and this is equal to KB dln omega and these are fantastic relations, isn't it? Because you see that what is omega?
Number of microstates.
Yes, so if you know the number of microstates, from there you can calculate the thermodynamic quantity. This is one, this is one, this one. And you will see later this omega has also another name. In microcanonical ensemble, this is called microcanonical partition function. Usually whenever people when refers to a partition function, they talk about canonical partition function, which we'll discuss later. But this is
Probably,
microcanonical partition function. Yes?
probably the constants in the second equation is like n and e, but instead of v and n. This is a
Which one?
constant in the second equation, p by t.
Yes, it should be
N and e instead of v and n. So, not that one, sir. That's
N
right.
and E.
Yes, sir.
Oh, this one. Yeah. That is a typo. Yes. Good. Yeah. We'll do it sometimes. Yeah, but you got the message, no? That from microscopic picture, you can calculate the thermodynamic quantities, and this is great. And this is the strength of statistical mechanics. Okay, but we'll now go deep into what is known as this omega. What is this omega? That we have to go. Okay, but before I do that, I'll talk about something which is known as Dirac delta function. And it is very important for this course, because if you don't introduce Dirac delta function, I cannot proceed. Going back to your Gaussian, going back to Gaussian distribution, if I plot this distribution, it looks like this. Hand drawn, of course, symmetric has to be. Okay, this is your exponential of minus x square by 2 sigma square, whatever. Is this fine? Now there is something called 3 sigma rule. How many of you know about it? Heard about it? Any idea about this 3 sigma rule?
So the total probability is between minus 3 sigma and plus 3 sigma?
So almost there actually. The idea is as follows. So your sigma could be like this. This is minus sigma, this is plus sigma, this is plus 2 sigma, this is plus 3 sigma, this is minus 2 sigma, this is minus 3 sigma. If you draw a vertical line at plus and minus sigma, this is not well drawn, but it will look something like this. And if I calculate this area of this curve, this shaded portion, you will see that between minus sigma to plus sigma, this area is about 68.2%, I think, of the total area. Was it done in some course, this 3 sigma rule?
In data analysis, we need it.
Okay. In the chemistry department?
Yes, sir.
Okay, good. So if I go to 2 sigma, which is something like this, and I calculate the area up to this, you know what is the answer? How much percentage?
25 point.
Hmm?
25 point something.
No, like total, it is going to be about 95%. Okay. And if I go to 3 sigma,
99.7.
yeah, it is 99.78 or something. If I go here, and I take this, this is 99.78%. Okay. So within plus minus 3 sigma, your distribution has almost completely decayed. This is about Gaussian distribution. Okay. This is called 3 sigma rule. But now if I have a Gaussian distribution which is narrower, what will happen? Same thing applies, but I can also have a distribution which is narrower. So actually in the limit, when your variance goes to 0, your distribution is becoming a function which is called Dirac delta function. How many of you heard about Dirac delta function?
Yes, sir.
Yes, sir.
Yeah. So basically, I can think of a situation. Okay, I have a Gaussian which is like this, and then I think of a Gaussian which is like this, and then one more. Okay, like this. So this is more like a Dirac delta. Okay. So it's a very narrow Gaussian. So in the limit, when your variance, your sigma, goes to 0, you get a Dirac delta function. In this case, this function will be picked at x equal to 0, and it is 0 elsewhere. So the function is defined in such a way that your f of x is actually infinity, because peak is infinity at x is equal to 0, other it is 0. And this function is called delta x, or Dirac delta function. And there are properties of this function. And mathematicians, they say this is not a true function, but for us, chemists, physicists, we are fine with this. And this is very useful in physical chemistry and physics. Okay? So now one property of Dirac delta function is that I can have a function which is not peaked at 0 but peaks at x. Okay, this is fine.
Yes, sir.
Now can anyone tell me, if I take a Dirac delta function and integrate over all space, what is the answer?
Unity.
I think it's normalized to 1.
Yeah, it is normalized to 1. Normalized. So then what is the unit of Dirac delta function? Dimension, rather.
1 upon length.
Yeah, so the dimension of Dirac is 1 over the argument, isn't it?
Yes, sir.
So if it is Dirac delta function in x, then dimension is 1 over x. But I can have a function in time, then dimension will be 1 over time. Okay, it is 1 over the argument. Is this clear?
Yes, sir.
Okay. So I can have few more property of Dirac delta function. So if I have an integral like this, some function of x times delta x, and I integrate this in the limit, what is the answer?
F of 0.
This is you should pick the function at x equal to 0. Similarly, if I have a function of, say, x, the multiplied with the Dirac delta function x minus a. Yeah, I should put dx. I had put dx there. I hope yes. And I integrate this. What is the answer?
F of A.
Yes, f of a. Now, delta of minus x. What is this?
Delta x. It's an even function.
It's an even function. Okay, this is quite important because this function will encounter this function again and again in many cases. Many situations will arise, will encounter this function. So now we go back and we are revisiting this omega microcanonical ensemble. This is important. But microcanonical ensemble, what does it mean? It means that if I have a Hamiltonian of the system, which is a function of your all momentum coordinates and position coordinates, this is equal to the energy, total energy, isn't it? This is a constant you have.
Yes, sir.
Now, this is your Hamiltonian is a function of 6n coordinates. This is fine. N is Avogadro number or even bigger. So it's a huge dimension. It's a 6n dimensional quantity, your Hamiltonian the function actually. So in one way of saying this, this constraint is like this. It basically means an equilibrium distribution probability distribution in microcanonical ensemble is has to be, it's a p equilibrium, whatever you want to call it. It has to be a function of h, you know, Hamiltonian. That is showed from Leibniz's theorem, no? Remember that?
Yes, sir.
So it has to be a function of h, Hamiltonian. And what kind of function of h? And what I'm going to do, it's a little abstract, and many books have many notations. I'm trying to collate all and use my own notation, and that is what I'm going to do now. Okay, because it is not straightforward in any book, and many has. So what I'm saying that for microcanonical ensemble, it is something like a constant. I don't know, some NC, some constant, some normalization constant times a Dirac delta function. This is very important physically. Which basically means when your Hamiltonian is equal to E, then only you take the distribution, otherwise not. Okay. Now, if I write this Dirac delta function, what does it mean? You have 6n dimensional phase space. In that phase space, actually you are considering a hypersurface in 6n minus 1 dimension, and any point on that hypersurface, okay, is a microstate. Any microstate lying on that hypersurface actually belong to that microcanonical ensemble. So you understand what I'm saying?
Could you
It's
repeat?
a constant hypersurface. You have 6n dimensional phase space. Okay.
Yes, sir.
And in that 6n dimensional phase space, you put a constraint that okay, I take only those microstates for which the energy is equal to the Hamiltonian, isn't it?
Okay.
Individual particle energies can change, but it will change in such a way that total energy, the Hamiltonian, is equal to the total energy, whatever the given energy. Which basically means in that 6n dimensional space, you have a hypersurface. Okay, and any point lying on that hypersurface would follow this constraint. So this Dirac delta function actually represents a hypersurface, 6n minus 1 dimensional hypersurface. Because, for example, if it is in 3D you have a sphere. Then what is the surface of the sphere? This is 2D. So if I call that the radius of the sphere is your E, capital E. Okay. Then any point lying on the surface of the sphere will have energy E.
Yes, sir.
And any point on that sphere is representing any microstate. So any microstate lying on that surface of the sphere, okay, will follow this constraint.
Yes, sir.
But it will have a 2-dimensional surface, isn't it? For 3n dimension space, it is 2-dimensional surface.
Yes.
So for 6n dimensional space, it will be 6n minus 1 dimensional hypersurface. Okay. Is this clear?
Yes, sir.
Got it.
It is abstract. N is huge, it's a Avogadro number. Very abstract idea. So actually, in other words, this omega is number of microstates, I'm calling it, no? Number of allowed microstates, isn't it? With that constraint, E. Is actually also proportional to the measure of the amount of phase space available, isn't it?
Yes.
Just think about it.
Makes sense intuitively.
Yes, it is. Yeah, you have to do like this. Now I'll give you a prescription. I'll stop here today. How to calculate omega. I try to find a rigorous expression for omega. Now, any suggestion? How should I calculate omega? Any idea?
Since rho, the function rho equilibrium has inside of it the Dirac delta, which
Yeah.
picks those microstates which are allowed.
Yes.
So if we integrate rho equilibrium,
Very good. Very good. So your omega has to be. Maybe I'll put another constant here. Some constant times I have to integrate this
rho
one, isn't it? What will be the integration limit? It will be over all phase. This is fine. So I am taking this and integrating with, and we will fix this constant. Okay, we'll fix this constant because I have to this constant. We'll see what is this constant. Okay. Now, how to evaluate this constant? Now, if you go back to quantum mechanics, restricts something. What is that? It says, okay, there is something called uncertainty between momentum and position. So it tells you that if I have uncertainty in momentum, say delta p, multiply the uncertainty in position, the corresponding position delta q, and this would be in the order of Planck's constant. This is the restriction put forward by quantum mechanics, as given by quantum mechanics, isn't it? This is called Heisenberg uncertainty principle. Okay, you know?
Yes, sir.
Yes, sir.
Okay, it's called Heisenberg uncertainty principle. So now think of the phase is fixed in dimension, and we divide the entire phase space into hypervolumes, each with volume d gamma equals to, not d gamma, delta gamma actually in my notation, equals to, and this volume is equal to h, okay, such that each of these hypervolumes contain only one microstate. You understand this statement, what I am saying here? So I start dividing the entire phase space into tiny volumes. And the tiniest volume I can have is what? Is delta sigma. Sorry, delta gamma, which is delta P times delta Q, which is equal to H. Because I cannot go smaller than this, because quantum mechanics restricts me to go smaller than this, because then I will violate Heisenberg uncertainty principle. Is this clear?
Yes, sir.
Within that volume, we can have only one microstate. Because within that volume, precisely, I can define only one microstate, isn't it? So within that volume 8, Planck's constant, I have only one microstate. Think about it. If it is not clear, tell me.
But sir, in classical mechanics, this can be smaller than h. In principle, it can be 0.
Yes, but end of the day, I have to go back to quantum mechanics, because I cannot violate quantum mechanics. Because this is how the subject of statistical mechanics is built. End of the day, you cannot violate quantum mechanics. You have to go back and fix your things. Cannot go entirely classical. It is semi-classical, I would call it. Okay, but if I follow quantum mechanics, which I have to, so end of the day, I have to take care of quantum mechanics, and as a result, I cannot have a volume element which is smaller than h. Is this clear? Because this is important, because from here in the next class we'll go. Like maybe I'll continue for 5 more minutes.
So these hypervolumes can contain one microstate only if they have an intersection with the hypersurface defined by the rho function.
Of course, with this constraint.
Yeah.
Okay. Of course, but this is a general statement, but the next statement would be that I do this only with that constraint. Of course. And that is the next statement. So if I now calculate omega, remember, this is the number of microstates. So it has to be this. Sorry, this has to be 3n, no, in 6n dimension. 1 dimension h. And this sum is taken over what? All the hypervolumes, no? But with the constraint, what is the constraint? That your energy is equal to Hamiltonian, but we say we allow a small, thick tiny shell around E, which is like E plus a small change in E plus E naught. Okay? So your energy is also measurable within uncertainty E naught. So this is also coming from uncertainty. You cannot energy is also because of quantum mechanics, this energy is also has some uncertainty. When you measure energy, you cannot measure with infinite precision. Okay, because of that, I put a small value E naught. It will be another shell, very tiny shell around E. Okay, so with this constraint, if I calculate this, sum of this will give you number of microstates for that microcanonical ensemble. These are accessible microstates, number of microstates. Any doubt? Ask me, because this is a very abstract kind of idea. Any doubt? Please ask me.
Hello. Yeah.
Yes.
Sir, the symbol that you have used, the lesser than symbol. So what does this signify in the summation part, hypervolume?
It basically means that your Hamiltonian has to be equal to E, has to be between E and E plus E naught. E naught is very small, okay?
Okay, so
Strictly speaking,
you are using
your
uncertainty in the
Hamiltonian has
energy.
to be equal to E. But
So
I
you are
say
using uncertainty in energy too. Like there's
yes. Nothing else. Yes. Okay. I'm putting uncertainty in energy as well. And this is obvious that your delta gamma is small. Interface phase, no? And if it is small, then what I can do? Then I can write this is almost equal to an integral, isn't it?
Yes.
Okay, I take this 1 over h to the power 3 and outside. Integral, and what should be the integral? Tell me. Of course, this integral is also taken with this constraint that it is e less than h less than e plus e naught. I did not write h. Okay, and this integration has to be over the phase. D gamma. Okay, so D gamma is actually sub. I should have put dot here. Okay. Okay. This is fine.
Yes, sir.
But now the next step is something like this. This one I approximate again. And it is not a bad approximation. I write this as did you understand what I did? We'll start from here next week. But maybe you have understood. So basically I approximate that volume by the area of the 6 and minus 1 dimensional hypersurface times the thickness of the shell, which is E naught.
Okay, sir.
You just think in 3D. You have sphere 4/3 pi r cube, no? Okay, 4/3 pi r cube. So this, if I do this, I can also write this as something like r squared dr, isn't it? With some constant.
Yes, sir.
Something similar I'm doing here. And while doing that, I'm not losing much. This is approximation, of course. We'll start from here because this is quite heavy and the ideas are quite abstract. But this is very important for this course. Think about it. And if you want to read this, I'll give you the name of the book. This is a book by Mark E. Tuckerman. Got the book or not? I don't know. It's called Statistical Mechanics, Theory and Molecular Simulation. A fantastic book, actually. Okay, I'm not writing the full name of the book, but you can find it out. It's Oxford University, Oxford graduate text, actually. It is there in the library. Try to get it. And with that, I'll stop today. Okay. And I'll stop recording as well. I hope you are following the course. Hope so.